I think that we are long overdue for a stupid pun. Electric fields. There's a lightning bolt, and then there's a field of grass. So this is our topic, electric fields. And it's gonna sound a little weird at first, but I think that we can make sense of it. And once we understand it, we can predict things like charge and force and motion for charged particles much easier. So let's start. And let's compare it to something we do understand, and that is gravity. So this is the Earth, and there is a gravitational field around the Earth. So if you think of putting different objects around the Earth, and you know that the Earth can pull those objects in with gravity, and an electric field, or in this case, a gravitational field, is like a map around the Earth that tells you if I put something here, this is what's going to happen to it, and it's a generalization of the entire thing. So if I put the moon right here, I know that the force is going to pull inward in that direction. I know that if I put the Earth there, it's going to be pulled in that direction, and then so on and so forth. And if I measure their distances from the Earth, then I can also know how strong the force is. And the reason why that's useful is if I do this in a bunch of different places, I can map out what the forces acting on any object of any mass around the Earth would be. So if I did that enough, it would look like this. I would have different length arrows, and I would have a bunch of arrows. And the lengths of the arrows are actually significant. So the longer the arrow is, that means the stronger the force is going to be. And you notice that the longer arrows are the ones that are closer in, and that makes sense because when you're closer to the Earth, the force of gravity is more. When you are further out, the force of gravity is less. And you can think of these lines as um, a model. And if I put an object on any of those lines, it's going to follow the path of that line. So if I put an object right here, it's going to follow that line that points towards the Earth. And that makes sense because if you put an object around the Earth, it's going to get pulled in by its force of gravity. Now, let's compare it to something we've just recently have learned. And instead of the Earth, so an object with mass, let's think of an object that has charge, and I'm going to call it Q. And you know that if there are charged particles and they are close to each other, then they exert forces on each other. And they exert forces in mathematically the same way as gravity does. So if I put a test charge right here, I'm going to call it a test charge. And I have a source charge right there. So capital Q, the big blob in the middle, that's a source charge. And the little dot on the right, that's a test charge. And we are going to say that the source charge is negative, and the test charge is always positive. This is just a convention that we use. And you'll see why we do this a little bit later. And if I put a positive test charge anywhere in this electric field, it's going to follow the lines that point towards capital Q. And if the source charge was positive, then that means all the arrows would just flip directions and they would all point outward. So it would try to push it away. Alright, so everywhere that I put an object, or anywhere I put a test charge, it's going to feel a certain force and it's going to go in a certain direction. And you can see once we map out the electric field, we know exactly what it's going to do. We know how much force it's going to feel, and we know what direction it's going to go in. And that would be for any charge. And that's why this is rather useful. So here's another example. There's a source charge in the middle, and let's say that it is negative so that all of our test charges will point inward. So it'll be a force of attraction. Then the way we define an electric field is you place a charge in the field and then you measure the force. And so the way we define an electric field is by a ratio. And so I put a charge here, And actually, I'm getting a little bit ahead of myself. Let me see what I have next here. Okay, yeah, so we know that the forces far away will be small, the forces will be large if it's up close. Okay, we already said that. Let's move on. So this is how it's defined right here. So an electric field is defined by the force on Q divided by Q itself. And so that small q here, that is, let me erase this, that small q is the test charge. Okay, I think I got cut off there as my battery was dying, but the point we were trying to make was this, that this is how the electric field is defined. It's defined by the force acting on a test charge divided by the charge. And that gives us a rather easy relationship to use to predict things like, in this electric field, if I put a charge, let's say I put a charge right there, then I know what the force is acting on it. And then from there we can do all of our normal physics. We can talk about how fast it'll go, how far it'll go, how long it'll take to go from A to B, etc. So the electric field is something that is constant, and by putting another test charge in there isn't going to change the electric field. So for example, if I put in a charge that was twice as much, let's say the first charge I put in was 1 coulomb and the second one was 2 coulombs, well, if it's 2 coulombs, then it's going to feel twice as much force, because we know that the charge and the force are directly proportional. So if I double the charge, then I double the amount of force. So the electric field is the same. So our model here that we're using actually helps us, actually makes a little bit of sense. So the electric field is defined by the source charge, not by the test charge. So by putting different charges in, it doesn't change it. So think of the electric field as something that remains constant, and then what you do is you put things in the field and then test to see what happens. And the idea of what the electric field is, and I apologize for that getting kind of jumbled, but this is what it says. It says that the electric field, it tells us the strength of the field due to a source charge. So it is a measure of the strength of the electric forces that are going on based on charge. Okay, now let's talk about a few conventions so that we are on the same page. Arrows will point away from a positive charge, and I mean source charge. So for example, if the source charge we have in the middle is positive, then the electric field lines will all point away. And that is because I use a positive test charge. That is the convention. We always use a positive charge. And if you think about it, it makes sense, because the electric field lines point in the direction of the force and what direction the object will go in. And if I put a positive charge near that big positive charge, it's going to get away from it, so it's going to point away. And just the opposite, if we have a negative source charge, then all the field lines point inward. Oops. Let me go back. Okay, and since our test charge is always positive, that means it's going to be attracted to it, so that means all the lines will point inward. Okay, so here is our definition. Okay, so the electric field is equal to the force acting on the source charge divided by the source charge. Or, excuse me, the test charge. And okay, so that's the force on Q. All right, we have talked about that already, and you know that if this is our electric field, then as I put objects in different places around it, we can predict what it's going to do, what kind of force it will feel, etc. Okay, now we can define the electric field in another way by combining it with Coulomb's law. So we said that it's the force acting on the charge divided by the charge. Well, the force given by our equation for Coulomb's law is defined like this. And the force is defined by Coulomb's constant K times both charges, so that would be the source charge for one of them and the test charge for the other, divided by the distance squared. So then we can also define our electric field like this, where we can substitute that in. And as you would see, that one of the charges would be canceled. And what we do here is we redefine it this way. So the electric field is going to be Coulomb's constant times the source charge divided by the radius squared. And so that actually helps us out a little bit. So before we put any charges near each other, if I just have one, then I can define it, test charge. So we have an electric field, and then we can explain what's going to happen by this relationship here. So I can put any charge anywhere I want, and then I can say, okay, how far away is it from the source charge? That's what the electric field will be. All right, so this is our new relationship. This is a new equation we are going to use. And I apologize if I made that confusing, so I'm going to reiterate that again. So our electric field is equal to Coulomb's constant times the test charge. And the test charge is the charge that we are going to put near another one. And then R is the distance from the source charge. But if that didn't quite make sense, that's okay. We're going to do a few examples later on, and it will solidify that. So here is another example of an electric field. And we got a positive source charge in the middle, and then I put a charge right there, and then we can measure its electric field. Another way to visualize the strength of an electric field is like this. You can draw a little circle in two places around the field, and you can get a sense of how strong it is by how many lines are in that circle. So if you're really close up, the arrows haven't really diverged much. So at this point, there's more lines so there's a stronger field. And that makes sense, because if you put two charges really close together, then their forces are going to be really large. If I take a little section further out, it's going to have fewer lines in there, and then it's going to have a weaker electric field. Alright, now, what happens if there's more than one charge? Alright, so we've got a positive charge and a negative charge. So what would the electric field look like in this situation? Well, if we think of what the forces acting on a test charge in different spots around here would look like, as in what direction would they go in, and then how strong would it be, then we can map out the electric field. So the easy point is right here in the middle, and if I put a positive test charge right there, we know that it's going to feel a force of repulsion from the positive charge, and then a force of attraction from the negative charge. So then overall, it's going to feel a force to the right. And if I put a charge right there, it's going to feel a force of repulsion in that direction from the positive charge, and a force of attraction from the negative charge. But then overall, if you add up those vectors together, it's going to go in that direction. Same thing if I put it on the bottom, except it would be on the bottom, but they would point right to the right. If I put one here off at a strange angle, it's going to feel a greater force from the positive charge because it's very close, and then a relatively weak force from the electric charge. So then its overall direction is going to be more up to the right. And if I used symmetry and looked at the other side, then it would be the same thing, but it'd be pointing more towards the the negative charge, so going down. And I can keep mapping out a bunch of different places all around the charges, and then you can generalize it and make a map. And that's what we're going to do, and that's what our electric field will look like. So put the positive one there, it wants to go that way. Alright, so we'll generalize it that between the two charges is going to be a straight line, and it points to the right, because it's going to push positive charges that way. Then if I put it up here, we're going to have, this is what we already talked about, it's going to have an arc that goes like this. So if I put a charge on that line somewhere, it's going to follow that line. And if you look at different points on there, it makes sense, because if I am right here, then it's going to feel attraction and repulsion, but in different directions. So up and to the right is one force, and then down to the right is the other force. And as I get away from it, those forces are going to change. So then, yeah. So then as we get further above both charges, it's going to follow this arc and this curve here. And then on the bottom, the same thing. So there you go. And you see I put some charges on here, those little black dots. If I put them in those places, I know exactly what path it's going to follow. And if I knew mathematically what the electric field was, I know what forces it's going to feel. So this is an easy way to predict what's going on. Okay, so here's our other example. It's really the same thing. But I want to emphasize the directions here. Because you remember that the electric field is equal to the force divided by the charge. And if you look at that, then it makes sense to say that the electric field and the force always point in the same direction. So this one has two forces. It feels one of attraction and a small one of repulsion. And so the direction of the force is tangent to that curve right there. So that electric field at that point will point tangent to that curve, and the forces will point tangent to that curve. Same thing if I put it out here. It's going to feel one force that way, one force that way, and then the total force is going to be tangent to the curve. And the electric field will also point in the same exact direction. Alright, so I'm going to skip over this because this is what we just talked about, but so you got one force plus two forces, and then the total force is going to be tangent to the curve. So what we just saw, this is a very specific thing. It's called a dipole. And they're two equal but opposite charges. So you might see this word dipole come up sometime, but don't get confused by that. It just means it's a very specific case of two charges, and they are the same amount. So if one is 10 nanocoulombs, the other one is minus 10 nanocoulombs. So it makes our electric field lines symmetrical. Okay, so electric fields, to summarize what we just talked about, electric field lines, they point in the same direction as the electric force. And we know that because E and F are directly proportional. So if you took a snapshot of an electric field over here on the right, where those arrows are, then it will be tangent to that curve. Okay, now I'm going to cut it off here because we're about 18 minutes into this video, and that was all of the theory. And what we're going to do in the next video is we're going to do example word problems. So we're actually going to practice using the equations so that you are a little bit more familiar with this concept.